All right, chemistry, this is your video lecture for section 3 of chapter 22. We're talking about nuclear radiation. Your objectives for this particular PowerPoint. I want you to be able to compare the penetrating ability and shielding requirements of alpha particles, beta particles, and gamma rays. Essentially, tell me what types of substances they can penetrate through, and what types of substances you would need in order to shield yourself from these different types of radiation. I want you to be able to define the terms Roentgen and REM, and then distinguish between them. I want you to be able to describe 3 devices used in radiation detection. And then lastly, I want you to discuss applications of radioactive nuclides. Now, as we go through here, there are going to be several very simple, general descriptions of these types of subjects here. Applications of radioactive nuclides, things like how they're used in medicine or dating. There are going to be 3 very quick descriptions of different types of instruments that are used in radioactive detection. All right, here we go.
Alpha, beta, and gamma decay can be compared on several levels. First, the penetrating power of the particle emitted by the decay differs for each type. Alpha particles are stopped by paper. Beta particles penetrate paper, but are stopped by aluminum foil. Gamma rays penetrate aluminum foil and are stopped by lead or thick concrete. Second, the change in atomic mass and number following decay also differs. Alpha emission changes both the atomic number and atomic mass of a decaying nucleus. Beta emission changes only the atomic number of a nucleus. Gamma emission changes neither the atomic number nor the atomic mass. Finally, the mass and charge of the emitted particles themselves varies. Alpha particles have a 2+ charge and have an atomic mass of a helium nucleus. Beta particles can have either a positive or a negative charge, but have a mass that is 7,000 times less than alpha particles. Gamma rays have no charge or mass.
Moving on to radiation exposure. Nuclear radiation can transfer energy from nuclear decay to the electrons of atoms or molecules and cause ionization. We've already talked about in class a very, very general, zoomed out description of free radical formation and the role that extra free energy plays in that process. Nuclear radiation is very commonly the source of that energy. The Roentgen is a unit used to measure nuclear radiation exposure. It is equal to the amount of gamma and X-ray radiation that produces 2 × 10⁹ ion pairs when it passes through 1 centimeter cubed of dry air. REM is another unit used to describe nuclear radiation, but a REM is a unit used to measure the dose of any type of ionizing radiation that factors in the effect of the radiation in the effect that the radiation has on human tissue. So we have 2 different units for radiation exposure, 2 different units for 2 different types of information being communicated. So make sure you're using the appropriate unit for whatever effect you're looking at that particular time. Here we have a table that tries to communicate the effect of whole body exposure to a single dose of radiation. So if your dose is somewhere between 0 and 25 rem, nothing's going to happen to you. No issue. If you're somewhere between 25 and 50 rem, you're going to have a slight decrease in white blood cell count. So this is going to result in, over time, you succumbing to common illnesses more regularly. If we go up to from 50 to 100, we're going to have a marked difference or decrease in white blood cell count. Here you're going to actually be becoming sick more often and more serious illnesses. If you're exposed in one dose to 100 to 200 rem, you're going to start feeling sick right then and there. This is a more stereotypical, more commonly understood side effect of radiation exposure. People, they become nauseous, they vomit, and their hair starts to fall out. Once you get up to 200 to 500 rem, that's when you actually start having ulcer generation. It creates ulcers, and you will start to bleed internally. Yeah, the small blood vessels that hold your blood together will begin to rupture, and you'll simply start to bleed internally. And once you start to get above 500, there ain't no coming back from that. Moving on to the devices used for radiation detection. The first one we're going to talk about are film badges. If we expose this film to open air or a particular area, we can measure the approximate radiation exposure of people working with that radiation. So this is a very common way for people working in radiation, under radiation exposure for whatever reason. It's a way for them to double check the amount of radiation that they're being exposed to at any particular time. We have Geiger counters. They're instruments that detect radiation by counting electric pulses carried by gas ionized by radiation. Remember that radiation, free energy, has the potential to ionize different elements or molecules. Well, the gas in the air, in the atmosphere, is elements and molecules. So if that gas is ionized, that ionization is going to have a certain amount of electric pulse associated with it, and the Geiger counter measures or detects those electric pulses. We have the scintillation counters. Scintillating light is a type of light that is created by ionized gas. Okay? We have an electrical signal that is created by ionized gas. That electrical signal can be converted into a light source, or not a light source, into a type of light. These instruments measure that light. So that is to say, substances that scintillate, absorb ionizing radiation, and emit visible light. So we take that. Again, the radiation is ionizing gases. That ionized gas is being scintillated and emitting visible light. We have another table here. These are the 5 generally accepted units that are used in measurements of radioactivity. Now, when you use these different units, you're going to be measuring something different, something unique each time. So we have these 5 units. We have radioactive decay. We have radioactive decay again. Those are different scales. Okay, one is very much larger than the other. One is smaller than the other. We have exposure to ionizing radiation. We have energy absorption caused by ionizing radiation. And we have the biological effect of the absorbed dose in humans. So this is the one that we are going to use for humans, for ourselves, more often, because we're talking about its effects on humans, its biological effects. So you hear this REM unit a lot more commonly when you talk about radiation exposure in populated areas. Radioactive dating is the process by which the approximate age of an object is determined based on the amount of certain radioactive nuclides present. The age is estimated by measuring either the accumulation of a daughter nuclide or the disappearance of a parent nuclide. For example, carbon-14 is used to estimate the age of organic material up to about 500,000 years old. This is the type of dating, carbon dating, that's has come under fire during different times in the recent past. But keep in mind, it's designed to be used for things that are already dead. They have to be dead, somewhere between 0 and 50,000 years ago. We can use radioactive nuclides in medicine. In medicine, radioactive nuclides are used to destroy certain types of cancer cells. For example, cobalt-60. These types of nuclides have so much free energy that they actually cause death in those cancerous cells. Now, the problem with this is that you can only apply them to a small area, because if you apply them to the entire human body, all of the cells in the human body will die, and that really doesn't do you very good in terms of medicine. Radioactive tracers. They're radioactive atoms that are incorporated into substances so that movement of those substances can be followed by radiation detectors. Radioactive tracers can be used to diagnose diseases.
Radioactive tracers are short-lived radioactive compounds. They are used in medicine to track biological processes. For example, a patient might inhale a light dosage of a radioactive gas. Because the amount of radioactivity is slight, it doesn't endanger the patient. The gas allows the doctor to see into the lungs. A special machine called a scintillator creates an image as it is struck by different intensities of radiation. Radioactive tracers can be used to locate tumors. They are also used to follow the path of drugs and other substances in the body.
Radioactive nuclides can also be used in agriculture. Radioactive tracers and fertilizers are used to determine the effectiveness of that fertilizer, much in the same way that you can track the uptake of certain substances in the human body, like we just saw using trackers. You can associate those trackers with a fertilizer and then track where those radioactive nuclides end up in some crop or plant matter. Nuclear radiation is also used to prolong the shelf life of food. Moving on to its waste. Fission is the primary process powering nuclear reactors. The products of fission include the nuclei as well as the nucleons formed from the fragment's radioactive decay. So not only do we have the daughter nuclei, we also have whatever else was chipped off or broke off of that parent nuclide. Both fission, like we see in power plants, and fusion, which we see in stars, produce nuclear waste. Fission, however, produces more waste than fusion. Nuclear waste needs to be contained so that living organisms can be shielded from that radioactivity, because all those negative side effects that we saw associated with living organisms being exposed to varying amounts of radiation. We have nausea, we have ulcers, we have death. So living organisms need to be shielded from that radioactive waste. There are two main types of containment: on-site storage and off-site disposal. The most common form of nuclear waste is spent fuel rods from nuclear power plants. Those fuel rods can be contained temporarily above ground in water pools or in dry casks, but that's just temporary. When we go to dispose of this nuclear waste, disposal of nuclear waste is done with the intention of never retrieving the materials. You bury it in a hole so deep, no one's ever going to find it. There are 77 disposal sites around the United States, where you just throw a bunch of stuff and hope no one ever finds it. There is a new site in the Yucca Mountain is being developed for the permanent disposal of much of the nuclear waste. So they're in the process of developing a centralized disposal site for these nuclear wastes. And with that, that's going to bring an end to our video lecture for this section. I will see you next period.